we start a set of information, set of lectures about the yarns, Yarns are very important objects in textile and very old objects in textile praxis. Around 25,000 years, the people society know to produce some yarns, so that it is very old and very original type of fibrous assembly. In my speech, I want first to introduce some general vision about the possibility how to model the structure of the yarn. Then we will speak about the special type of models, so-called helical models of the yarn. Then something about the alternative to helical model, which is called as a migration model of the yarn. Well, let's start this general introduction part. On your picture is a scheme of some general yarn with one red fiber inside. The fiber in the yarn is have a very complicated shape, and we must use some coordinates for description of this shape. Usually we use a cylindrical coordinates R. Maybe this is some general point on the fiber. R is radius, angle phi, and the length zeta. The shape of the fiber in yarn have in the same moment random character as well as the general deterministic trend. You know it intuitively that the general trend is similar to helical trend, isn't it? Well, let's think a little about one fiber element inside the yarn. This is yarn axis, and this red part is some general fiber element. The distances are here from R to R plus dr. This angle is d phi, so that this length is R times d phi, and the height is d zeta. Using these lenses, we can define three angles which are here. Angle alpha on the green wall, angle beta on the yellow wall, and angle gamma on this violet wall. It's evident that these three equations are valid, and from the three, it's evident that also is valid that tangent alpha is tangent beta times tangent gamma. Yes, some small note. It's evident that this angle beta relates to the yarn twist intensity. We will speak about it later. It exists also a second possibility, second triplet of angles which can characterize our element. There are the angles theta A to axial direction, theta R to radial direction, and theta T to some tangent direction. From this picture, you can see what is theta R, theta T, and theta A. And evidently, based on Pythagorean theorem in three-dimensional space, this equation must be valid. After dividing by dl, we obtain this, so that we obtain this equation, which is very known rule of direction cosinus. Okay. From definition of all angles, it's evident that following expressions are right. We can also define the length of our red fiber element, which is this here, d zeta times this here. After rearranging, we obtain this equation. The relation so that the relation between angles theta, theta t, and theta a are given by this triplet of functions. No too difficult. It's only the describing of geometry of fibrous element. It's evident that two independent values define the direction of fiber element. We use one value d phi by d zeta and the second dr by d zeta 2. Let's define d phi by d zeta for one fiber element. Let's call as a value 2 times pi times z, where z is, we can call as a twist of element. Later we will explain it more precisely, why it is. This twist of element can, but needn't be identical with yarn twist, which we know from technological terminology. So, from so defined equation, z is d phi by d zeta by 2 times pi. We can multiply and divide by here blue value r. And this was tangent beta. So z is tangent beta by 2 pi r. Yeah? Well, the second characteristic is the characteristic of, the first one is characteristic of twist for our fiber element. The second characteristic, dr by d zeta, which is m, is a characteristic of radial migration. Evidently, going back to our equations about angles, we can write also that this m is same than tangents alpha. This couple of two, I must say that we conventionally use d zeta, so increasing of vertical coordinates, as a positive value. Yeah, elemental but positive. We assume that our zeta coordinate is increasing when we are some like a microbe, and when we go through this fiber path inside of the yarn, then our zeta coordinate is higher and higher and higher and higher. Okay? So using these two parameters, z and m, 4 possible characters of fibrous element can be defined. It's shown here. I said that we assume that all that zeta coordinate must every time increase. In our this is the graph radius of fiber points and zeta direction. It is possible that generally that the fiber can go also back, some loop inside of the yarn. Yeah. So how to explain it when we said that we want zeta value have only as an increasing coordinate? It's easy. Let's imagine that we divide our fiber so that we obtain this part, then this blue part, then this red part, and then this blue part to some segments, and on each such segments we can imagine that the zeta coordinate is increasing. Yeah? So that our assumption about the increasing value of coordinate zeta is possible to accept also generally for each fibers. 3D-dimensional part of a general ith fiber, some fiber, one fiber in yarn structure, let's call it ith fiber, yeah, general ith fiber, be determined by two differential equations. Because d phi by d zeta is 2 pi z, but this z for ith fiber is changed from point to point on the fiber, from element to element of our ith fiber. Yeah? So this z, zi, is some function of zeta. Yeah? From this, after small rearranging, we obtain d phi is 2 pi zi zeta times d zeta. Similarly, also the quantity mi is changed on the path of our ith fiber. Therefore, it must be a function of zeta. So, from this is valid that dr is the function mi zeta times d zeta. This couple of two, formally very easy, but both are differential equations, isn't it? Yeah. This couple of these two differential equations define the three-dimensional path of a general ith fiber. Well, and now we have two possibilities how to create a model of the yarn. The first is to interpret the fiber path as a stochastic process. Let's imagine two set of fibers inside of yarn exist a set of functions zi, zeta, over all I, for first fiber, for second fiber, for third fiber, and so on. Each such function is a little larger. It's individual to disordered fiber. So that the set of such functions can be usually interpreted as a set of realization of a stochastic process. And similarly, also the set of functions mi zeta over all I can be interpreted as a stochastic process. And the path of fibers in yarn can be interpreted as a stochastic process. Okay? So that each fiber is a little larger, random, oriented, no same one as the other. If it is so, then we need to use for evaluation of the yarn structure the tools related to stochastic processes. It's, for example, correlograms, or maybe you heard about the parameters from Professor Hierl, fiber mean position, RMS deviation, and mean migration intensity, and so on and so on. These all are tools how to evaluate the random process. Also the period of migration and so on. It is one way, no too easy. In our lectures we will not do more discuss this direction. Second concept is to interpret the fiber paths as a deterministic process. Individual fiber paths have usually a random character, but their dominant trend is commonly deterministic. For example, helical. Therefore, we often substitute the real fibers by an ideal representative fiber trajectory around which the real fiber paths are, we can say intuitively, oscillated. Okay? Then, based on our function zi zeta, mi zeta, this couple of these functions must be deterministic, no, probabilistic. If mi zeta is not equal 0 for all fibers, for all I, what is it? M was dr to d zeta. If it is not equal 0, then the radius of fiber path is changed, isn't it? We speak about the radial migration of fibers. If zeta is different from constant, z was d phi by dz. angle, increase of angle by zeta coordinates. If this value is not constant, then the local twist, the twist of fibrous elements, is from point to point another. So that we must speak about a twisted migration of fiber. And if both are well, then we must speak about the general migration of fibers in yarn. In opposite, if each mi zeta is equal 0, if each zeta zeta is the same constant, we speak about non-migrating or helical model. And it brings us to this table, which can, in short, to classify the lot of different types of models of the yarn structure to in some system. First group are the stochastic models. We don't want more to divide this possibility. The second group is the deterministic models, and it based on the character of function zeta and mi zeta. If both are equal, what it means, radius is stable for each fiber. dr is not different from 0. And d phi by d zeta is also 0, so it is bundle of parallel fibers. Parallel fiber bundle. If z function is equal 0, but m is different from 0, that fiber have not twist, but the fiber is on different radii. Then this is something like entanglement bundle. If z is constant and m is 0, it's our known helical model. If z is constant and m is not 0, then it is the traditional radial migration model. For example, like Triller and Tada. If z is not constant and m is constant, then the fibers are lying on some imaginary cylinder every time, but on the cylinder they don't create helix, then some other curve. We can speak about the twisted migration. And the last position is if all is possible, and this is the general migration. We will speak, we will in more details speak about these three. About this is not necessary more speak. Bundle of parallel fibers was in our earlier lecture. So that two versions are important for us, helical model at most, and then also the radial migration. Yes. So it was a small introduction to how to in general to divide different types of models of yarn structure. Now let's speak about the helical model of the yarn. We said the helical, each model is given by two differential equations. This is the first and this is the second. It is the same as was. In helical model, this function zi zeta is constant for each fibers and each point, each segment, each element on each fiber. This constant have name z, it's constant, and I will through some one or two slides to show you that it is a twist of the yarn. The second, on the second equation, this function m zeta, mi zeta is equal 0. What we obtain? When we obtain from this first equation when this function is equal z. Let's integrate this equation so that integral over phi from some starting point coordinates phi 0, zeta 0, r 0, yeah? From phi 0 to phi is equal to integral from zeta 0 to zeta on the right hand side. But this function z is constant, therefore we obtain this here and then this here. What is it? Zeta minus zeta 0 is increase of zeta coordinate, axial coordinates in the yarn. Phi minus phi 0 is increase of angle phi. Divided by 2 pi, 2 pi is 1 times round. So it is number of coils, isn't it? Number of coils by corresponding lengths is the definition of twist. Is it so? Well, so such constant z have the sense as a yarn twist. So that also the height, axial height per one coil must be 1 by z, evidently. From the same equation, we can write also, this is valid, now z is constant, it's not a function as a general. It's constant, after multiplication and dividing by r, we obtain this here, but this is tangents beta. So tangents beta is 2 pi r z, okay? And from the second equation, from the second differential equation, after integrating from r0 to r, here from zeta 0 to zeta, for starting point to some general point, we obtain what? Because this is 0, then r minus r0 must be equal 0, so r is equal r0. What it means? The fiber is lying on the same cylinder by the given fiber is lying on the cylinder with constant radius, of course. Yeah? R is R0. Each R is R0. Okay. There are these two equations are basic equations for helical model. But we can also to interpret this helical model very easy. We can say this is some scheme of the yarn according helical model. On the general cylinder diameter R is lying one red fiber. This length is 1 by z. Angle of between the tangent to our fiber and vertical direction is an angle beta, isn't it? And after unrolling of this surface of such imaginary cylinder, we obtain this triangle. From this is also possible to calculate that tangents beta is 2 pi r by 1 by z, so 2 pi r times z. Well, the solving of differential equation need every time some starting point or something so. Our starting points from our fibers based on packing density. If some fiber is starting from some radius, then this fiber is lying on this radius and have a part to the total packing density on this radius. Yeah? How is the packing density? So much fibers can be on this or that radius r. Generally, the packing density is a function of radius. And based on experimental experiences, when this is radius and this is packing density, then the real curve is something like this black curve on our small picture. But it is difficult to obtain such function. We can obtain or experimentally, based on no too easy experimental process, or make some mechanical model of the yarn, also not too easy. Therefore, we often use a fourth assumption for simplification of our problems. We assume in that fourth that the packing density in all places inside of the yarn is constant, like this red line, red horizontal line in our graph. Okay? Well, when also this assumption is valid, then we will speak about the ideal helical model. Yeah? Helical model is without this assumption. In ideal helical model, we accept also this assumption. The helical models and ideal helical models are in a lot of publications. Some of known authors I mentioned here, from Kechlin, 1828, to Triller, which completed this helical model in a relatively complete concept. Well, this is the, I can say, definition or description, what is it, a helical model. In our helical model, let's find the number of fibers and then also the shortening of the yarn due to twist. The first theme will be number of fibers in cross section of yarn, ideal yarn which corresponds to our helical model. So let's imagine some cross section of the yarn. The cross section of the yarn is here, yeah? The gray islands here represent the sectional islands of individual fibers. We create two circles here, two green circles here. The smaller one have the radius r, and the higher one, the larger one, have the radius r plus dr, plus differentially elemental increase of radius, so that we obtain a differential annulus, isn't it? Differential annulus. How is the total area of this differential annulus? No, it's evident because it's differential annulus. It's 2 pi r times thickness. When you cut it, this you obtain some long, and it's intuitively clear. 2 pi r times dr. How is the area? How is inside of our annulus the area of fibers? It is here as a red area. No whole area of such annulus is the area of fiber section. There are also some air parts here, isn't it? Well, but you know what is it, the packing density? So that the area of fibers, ds, must be 2 pi r dr times mu times packing density. Well, and we will need also an older and for us known relation that the sectional area per one fiber, which is lying with his axis on the radius r, of course, is cross-section area by cosinus of this angle beta. Okay. Now is the question, how is the number of fibers in differential annulus? To solve this problem, let's imagine one abstract situation. Let's imagine that I am not here, nobody of us is here in this room, and I am standing here. One foot is inside of room, the second my foot is outside of this room. How many people is here? Maybe 1/2, because I am here only 1/2. Do you understand it? Yes. Well, you can see that number of fibers needn't be only 1, 2, 3, 4 natural number. Then it can be a real number. For example, 1/2 or something so. Second, how many people is here? We can calculate 1, 2, 3, 4, 5. But I have another idea. Let's go all together to some weighting machine for tracks and so on, and we will find our common weight, and then I will divide this weight through mean. Of course, mean weight per one person. Is it possible this way, logically? Is it possible, yeah? Well, we will use this style of thinking. Fiber area in our differential annulus is ds, okay? And area per one fiber is S star. S star. So the ds by S star must be number of fibers in our differential annulus. Using equations derived, we obtain for dn this formula, this expression. And now, how is the substantial cross-sectional area of yarn? Substantial cross-sectional area of yarn is this our red area in earlier, but integral of this, sum of this over all possible annula. They are from r equals 0 to on the periphery r equal d by 2, 1/2 of a yarn diameter. So that it is this here, using as we created, we obtain this equation. Mean packing density of the yarn, it is total, it's substance cross-section of the yarn by total area of cross-section of the yarn, pi d squared by 4. After rearranging, we obtain this here. Number of fibers in yarn cross-section, no, it is integral from this dn of number per one annulus. From r equals 0 to r equal d by 2. After using it, we use here some geometrical formula, which you know, 1 by cosinus square is 1 plus tangent square. And after small rearranging, we obtain this here, because tangent is 2 pi rz, we said, yeah? Tangent beta. Well, but it was also derived in our lecture 1, starting lecture to structure, that number of fibers is tau times kn, where tau, relative yarn fineness, is the ratio yarn count, more precisely, for example, in text, linear density, yeah, by fiber linear density, fiber fineness, yeah, yarn fineness by fiber fineness. Okay. Coefficient Kn, which is in this expression, can be derived from this as n by tau. Tau was in our lecture 1 also capital S by S times n, and we know, so that we obtain this expression for Kn. These expressions are valid for a helical model. It means, therefore, I have mu inside of integrals, because mu can be a function of radius. I spoke about the difficulties with them, so that let me now to make this or rearrange our equations. For the case of ideal helical model, it is what? It is the model on which the packing density in all places inside of the yarn is constant. Therefore, mu is possible to give before integral as a constant. Yeah. Well, how is substantial cross-sectional area? Mu is going before, so we obtain this here. The end formula is this here. Now, evidently, PD squared by 4 total area times mu corresponds to our knowledge. Mean packing density, we derive this equation times mu is constant, so before integral for r dr, it's trivial, so that we obtain mu final position mu bar equal mu. Now, evident, if mu is constant, then each local mu must be the mu for whole yarn. For a future rearranging, we need to solve one integral. This integral is shown here. It's shown also the way how to obtain it. It is not too difficult. Use such substitution and you obtain this result. So I think I don't want to comment the integration. Yeah. Well, a number of fibers in yarn cross section. For this we had this expression. Now mu is constant, can go before integral. We obtain this expression. But this is our earlier integral, this one. On the place of this we can give this expression in brackets. And after small rearranging, where we use, here is, we multiply and divide by d square, then we understand that this is S, capital S, so that this is tau, you know, it is earlier equations, trivial equations. We obtain number of fibers in this form. Yeah? And Kn because it's n by tau, Kn is given by this equation. We can also use another rearranging. This expression is identical with this expression. But we know from lesson 1 that pi dz is tangents beta d, tangents of peripheral angle beta on the yarn. So it's tangents beta d. After a rearranging, where we multiply and divide by 1 plus cosinus beta d here, we obtain finally Kn in this form. Only rearranging, pure trivial mathematical rearranging, which you know from university, from high school. No difficult. Okay, how is Kn graphically? How is Kn when we use this last formula for Kn or express it in graphical form? We obtain such graph here. This is axis of peripheral angle beta d, and this is axis of value of Kn. We obtain this thick curve. In the textile praxis, usually we twisted the yarn so that the peripheral angle is something between 20 and 30 degrees. So let's imagine the average value 25 degree. This is this red dotted line. To this angle corresponds the coefficient 0.95. When we experimentally measured coefficient Kn, or evaluated based on cross-sectional, microscopic preparates cross-sections of yarns, then really we obtain the value around 0.95 for yarns, ring spun yarns. No for rotor yarns. For rotor yarns we obtain much more smaller value because the angles of fibers are not in dominant effect created through twist, but important is also the intensive unparallelity of ribbon and rotor, and so-called bridge fibers on the periphery of rotor yarn. You know this term, you know this problem. So that in rotor yarn, the coefficient Kn is smaller. Well, this is all for coefficient Kn. The theoretical value of this coefficient based on ideal helical model. In reality, it can be a little harder. Why? Because the structure is not perfectly ideal helical model. Well, to the problem of number of fibers and coefficient Kn, related also the theme about the yarn retraction. You have an individual experience, intuitive experience. When you twisted something, some bundle of something, maybe fibers, maybe also a bundle of yarns or something so. Then when you twisted this bundle, the bundle is shorter and shorter and shorter and shorter and shorter, isn't it? And in one moment it's not possible more get the twist inside. Okay, it means by twisting the fiber bundle is shorter and shorter. Let's imagine some bundle of parallel fibers, which is here, length zeta 0. After twisting, the length of resulting yarn is zeta smaller than zeta 0. This length zeta 0 minus zeta, it is the difference of length between a non-twisted and twisted form of our bundle. This column here represents non-twisted structure, this structure. The second column here represents twisted structure, this structure. Yeah? So, length of bundle in non-twisted bundle is zeta 0, twisted is zeta. Yarn retraction we define as ratio zeta 0 minus zeta, this length, by starting length zeta 0. So that we can write it 1 minus zeta by zeta 0. Yeah? Yeah. Number of fibers by twisting is not changed. So that here is n and here is also n. Volume of fibers, generally, we can say that it can be different. Total volume of fibers can be different in this bundle and in this bundle. Therefore, starting value is V0, final value is V. Mass of fibers must be same in non-twisted as well as in twisted structure. A starting count of or fineness of parallel fiber bundle is mass by length. Mass is m, length is zeta 0. So starting yarn count T0 is m by zeta 0, isn't it? After twisting, I will in short say yarn count, I mean linear density, for example, by text and so on. The yarn count is now m by another length zeta. The relation between T0 and T, based on the definition of yarn retraction, is this one. Number of coils in parallel fiber bundle is 0. Here number of coils is NC. And we can construct we will construct two quantities for twist. The first, which is here, it will be latent yarn twist. It is number of coils per length of starting non-twisted structure. Yeah? How many coils I will give to 1 meter of non-twisted parallel fiber bundle? Do you understand this term? In opposite to standard yarn twist, which is the same number of coils, but by length of yarn. How many coils is on 1 meter of yarn, final yarn? So that it's NC by zeta. Between latent yarn twist, Z0, and yarn twist, real yarn twist, Z, related to this relation, this expression is valid. Latent twist coefficient. We can consider also the latent twist coefficient, which is Z0 times square root of T0. latent twist and starting yarn count. In opposite to twist coefficient real, which is z times square root of t. Yeah? So these latent quantities related to starting lengths, no to final lengths. There is this difference here. Yeah. It was starting quantities. Now in a set of our slides are 3 versions of model for yarn retraction. We will comment only the second one. We will jump the first one and the third one. It is not too necessary to say it here. When somebody will study deeper the problem of yarn retraction, he can use my slides and immediately from these slides to understand also the first and the third version. So the first version, it is idea of neutral radius according to Obuch or Bassett. We will not to do it. We will start with version 2, the second variant of model, idea of total fiber volume, which was created from Brushler around 1935. It was some specialist about textile on the university in Switzerland. Well, but how is this theoretical concept? I want to show you in the next lecture. So, in the moment, thank you for your attention.